Hello everyone to the third installment of the basics part of this Save My STEM Physics channel. This I believe will be the last part in the basics section. And this is a lesson on linearization of graphs, something which will become very useful for you in required practicals, something we generally won't go over on this channel, but something which is undoubtedly very useful for you. Now, what does it mean to linearize a graph? Well, a linear graph is just any sort of straight line graph. So that is probably about y equals 3x plus 1. Or we could have a negative straight line like that. And that would be about y equals negative x minus 1. So a linear graph is any graph that is a straight line. However, if I have a graph like this, a parabola, y equals x squared, that ain't a straight line. And it therefore has a different gradient. Notice how I'm drawing tangents on different points to represent a gradient. That has a different gradient at every point. But well, there's no such, well, what I'm trying to say, sorry, is the gradient on any straight line function is constant. So, why do we want a constant gradient? Well, we can have graphs. Why don't we take Newton's equation F equals ma, Newton's second law, and plot F against acceleration? The mass, therefore, is going to be the gradient. So F over A equals m, m being the mass, force is F, taking delta y, if this is our y-axis, and acceleration being delta x. So change in y over change in x is gradient, so F over A is m, and that gives us the gradient of the line. Simple enough. Or you can't see that, I just realised. That's what I've been drawing at the bottom there. We have a straight line graph for F equals ma, and we have those sort of ideas. Now, what if we have, what if we have an equation like, you won't necessarily know about this equation yet, but if we have n lambda equals d sine theta, this is to do with diffraction, so how light interacts when passing through a diffraction grating, passing through many slits of an even slit separation. And what we'll notice is this graph, due to it being sine theta, is not going to be a straight line. Now, this function, this equation only exists for theta less than 90. So we'll just do 90 degrees of a sine graph. So if we plot the order of spectra, which is n, and rearrange for n, you get d sine theta over lambda, d over lambda sine theta. Sine theta is what we're changing. The d is a slit separation, and lambda is wavelength. You don't need to know about that for this lesson in particular. This is just an example, and the sine theta is obviously going to change with the angle. However, sine theta does not go up proportionally, so it will be a graph that looks somewhat like this. And again, that is not a straight line if we plot it against theta. However, if we do the exact same thing, n lambda equals d sine theta, and rearrange to get lambda equals d, sorry, n equals d over lambda sine theta, if we instead plot sine theta on our x-axis and n, we then get a straight line. So all we are doing is we are rearranging so that we have a y term, which should ideally be just by itself, and then we are going to get any function on the other side and plot this on our x-axis. So the way we can think about it is we can think about our equation of a straight line, y equals mx plus c, and we can map everything to something. So n is our y, m is d over lambda, x is sine theta, and there's no constant term here, so we can imagine that's plus 0, and plus 0 is our plus c. So that's how you can imagine it. So now, instead of plotting y on the y-axis, we're going to plot n on the y-axis, and instead of plotting x on the x-axis, we're going to plot sine theta on the x-axis. And hopefully that has made enough sense for you guys. Hopefully it's been a relatively short video, and hopefully that explains all you need to know about linearization of graphs. Post video here, I've just been doing the editing for this video, and I've realized I've forgotten to explain something very crucial about why this specifically, and therefore many other cases, in many other cases, it's very useful to linearize a graph, because obviously I've already spoken about how it will provide us with a constant gradient, but why exactly do we want that constant gradient? We want that constant gradient because you notice that we have our m, our value for gradient here is d over lambda, meaning in a practical where you can measure the slit separation d can be measured. So, for example, you may have slit separation of, say, 2 times 10 to the minus 4 meters, and you can measure that using a traveling microscope. However, with light of wavelength lambda, you can't exactly measure that one using a traveling microscope. You can't measure that doing anything, right? So that means that using our now straight line graph, which should pass through 0, 0, although importantly when doing a line of best fit of results, don't force it to go through 0, 0, force it to be roughly equidistant from points, and therefore you can determine that delta n over delta sine theta, so that's the same as change in y over change in x, equals d over lambda. D is a known term, so you can rearrange it to find that lambda equals d over what I'm just going to call m, which is the same as delta n over delta sine theta. This allows us, using linearization of graphs, to determine a mean experimental value for lambda or any other physics constant which we may be trying to determine. Thank you.